All right, so today I want to look at two things. What is a separable differential equation and how do you solve one using separation of variables? Also, what is a linear first order differential equation and how do you solve that by integrating factors? And we'll have more techniques for solving differential equations, but right now I want to look at these two. So first off, let's do number one, our definition, a first order. And here everything is first order right now. So a first order differential equation is called separable if and only if it can be written in the following form. dy dx equals function of x times function of y, right? If you can separate it by factoring, right? So function of x times a function of y, then we call a differential equation separable. Such a differential equation can be solved basically by integrating both sides. All you have to do is divide both sides by g of y and integrating both sides with respect to x. So specifically, all you're doing is you're dividing off the g of y. Right, so you have 1 over g of y times dy dx equals f of x, and then just integrate both sides with respect to x. So you have integral over here, g of y, dy dx. Right, you're integrating that with respect to x. And then you're also integrating the right-hand side with respect to x. All right. But now look at the left-hand side. On that left-hand side, you have an integral of a function of y, namely 1 over g of y, times dy dx, that integral with respect to x, right? So at the end of it, even if you don't know what that function of y is, you could say by the chain rule or by u substitution. What does it become? It just becomes the integral of g of y with respect to y. Right? If you want to think of it as the dx's canceling, that's a nice way that the notation is built to sort of make the right things happen. But you can also think of it just as, you have some inner function and you're multiplying by the derivative of the inner function, y, and then dy dx, right? Is what's going on there. So that's our process. Then, then from here, what you get, you just evaluate the integrals. And when you evaluate the integrals, you'll get at least, if you can evaluate the integrals, right, you'll at least get an implicit solution, meaning an equation involving both x and y, but maybe they're all tangled up, right? So then typically, you at least try to solve for y. Then, and maybe the algebra is too weird. Maybe you can't do this, but typically you try to solve for y to get an explicit solution. So that's our process of how to solve via separation of variables. Let's look at this in an example. So in my what is differential equations video, we looked at this differential equation. Right, let's solve this using separation of variables. So here, I'm going to say that first notice it is separable because that right-hand side factors, right? We have f of t is 2 and g of big T is t minus 10, right? So it is separable. That it's already written as a factorization of a function of little t times a function of big T. And again, here, of course, I'm using little t and big T as opposed to x and y. But just think of it as dependent variable, independent variable. It doesn't really matter what letters they are. Right? The process is the same. So here, then I can follow the little algorithm, right? So divide both sides by g and integrate both sides, right? So when you integrate both sides, the little dt's are going to cancel by chain rule, u sub, whatever you want to call it. Right, so integrate both sides. We get log of t minus 10 equals 2t plus some constant of integration. Right. Now, this, you could leave it right like this, and this would be an implicit solution. You can even check your solution using implicit differentiation, right? So this is a perfectly good stopping point. But here it would be sort of sad to stop there because we could go further, right? So we can do, we could try to solve for big T. So take e to both sides. Right. Get rid of the absolute value with a plus or minus. Add the 10. And then I want to also use some properties of exponents to break up that e a little bit. Make it e to the c times e to the 2t. Because I want to make a substitution. So I want to clean up that constant, plus or minus e to the c, right? Call that just c. Because plus or minus e to the c, it doesn't have any little t in it at all, right? So it's just some number. It's just some constant. So just call that number c. Right? So this becomes right, big T of t equals 10 plus c e to the 2t. Great. This is the general solution, right? So this is the general solution. So we got it via separation of variables, right? Where c can be any real number. Now there is a skeleton in the closet here. So be careful at this step right here where we divided. Note that we have an assumption. We're assuming that t is not just 10. That t isn't just the function 10, right? If t was just equal to the constant function 10, then we can't really do that step. It doesn't make any sense because we're just dividing by 0 then, right? So that step works as long as t is not equal to 10. So how does that kind of propagate through here? Well, that would be the same as down here, right? That would be the same as saying that, noticing that this e to something cannot be 0, right? Which, this coefficient being 0, that's the same condition as t being 10. So that's how it kind of traces through in the algebra there. Now here, this c can be 0, right? So, just be careful. Did you introduce a new solution when you renamed it? Well, yes, you did, but we want that one, right? It's good that we did because 10, the constant function 10 is a perfectly good solution to this differential equation. So it's a little bit subtle, but It's at the end of the day, right? That is the general solution. So that's separation of variables and an example of solving a differential equation using separation of variables, right? So that is our first thing on our to-do list. Then I want to also define a linear first order differential equation. They're all first order, right? This is in this part of our discussion, but linear, we haven't defined linear yet. So let's look at that now. So part 2, let's look at a definition, right? We want to define a linear first order DE. Is an equation, differential equation, that can be written in the form dy dx equals p of x times y plus q of x. So this is our definition of linear. How to solve this? Do something that's going to look very much like a rabbit out of a hat. So this is what's called an integrating factor, meaning just something that you multiply both sides by to be able to integrate the equation. So multiply both sides by the integrating factor, which often is written as mu. It's mu of x. E to the integral of negative p of x dx. Right, so I didn't show at all where that formula comes from, why that's a good idea, but you'll see in this video, you'll see that it works. Also, if you stick around for our primary source projects, you'll see historically where that comes from, that it comes from the work of Leibniz, Bernoulli, Euler, big chain of people kind of danced around this idea for a very long time. But for now, I'm just sort of saying, hey, this is a good idea. This is the method of integrating factors, right? And we're gonna try this out in an example. One note here. So note in the exponent there, when you do that antiderivative, just use an antiderivative. You don't need the most general antiderivative of negative p. Antiderivative, there we go. Right, meaning no, you don't need the plus c when you do that integral. You just need an integrating factor. So maybe I should write an integrating factor, because it doesn't matter which antiderivative you use in that exponent. So, all right. So that's our method. Now, why does this help? Right, I didn't say why this helps. So multiply both sides by that integrating factor. It turns out once you do this, the left-hand side will become the derivative of mu of x times y. Will become just that, just the derivative of mu of x times y by the product rule. And that's what's going to clean up your equation and make it solvable, right? So it's going to make you able to integrate both sides. And here it might sound a little bit cryptic. I think it makes a lot more sense in an example. So let's do that. Let's go to an example. Let's do actually the same example. It turns out it's linear, right? So the equation dt 2t minus 10, right, is a perfectly good linear in first order, right? because you can expand out that 2. So we have 2t minus 20. So p of t in this case is just 2, and q of t is minus 20. Right? So that's the reason this is considered a first order linear differential equation. Now, from here, I have to multiply both sides by the integrating factor, mu of t, right, which is going to be e to the negative integral of negative 2 dt, right, e to the minus 2 t. This is what I want to multiply both sides by. Right, so let's see what this becomes. So e to the minus 2 t dt dt, and 2e to the minus 2 t t, and minus 20 e to the minus 2 t. And now I promised that the left-hand side would clean up with the product rule. Right? And it does once you give it this other piece. So subtract the t term over to the other side. Right. So the term q, right, the q term, that will stay on the right-hand side, but the term with p, subtract that over to the left-hand side. And maybe I should actually mark that up here. Then, right, so after you multiply by the integrating factor, it will, the left-hand side will clean up, but it needs the p term over there, right? So subtract also the p term over to the left-hand side, right? So only the q is on the right-hand side still. Then what happens? Well, right here, this is maybe the trickiest part of this. Notice by the product rule, this is just mu times your unknown function times big T. All right, that left-hand side cleans up with the product rule. Why? Well, look at it in reverse, right? How would you implement product rule if you took this derivative? Well, the one thing you would do is you'd leave this e alone and you would differentiate the t, right? That's one term in a product rule. And then you do the same, but in the other order, right? You would leave the t alone and differentiate the e, and then the chain rule spits out a -2. So there we go. They're equal, right? So the left-hand side is equal. It's just a little awkward because we're used to taking a derivative and expanding it out into two terms using the product rule. Here we're kind of doing the other way around, right? We have those two terms and we're collapsing it into a derivative using the product rule. But equal is equal, right? You can use it either way. So now we can integrate both sides, right? So integrate both sides. And when you integrate both sides, on the left, the derivative just goes away, right? On the right, well, now we need to actually do an antiderivative. Right, so I get the antiderivative of e to the minus 2t, means I divide by -2. Also, I get a plus c because I just integrated both sides. All right. Now, once again, you could stop here and you have an implicit solution, but it's not too much work to solve for big T. So let's do it. Let's get an explicit solution, right? Let's do a little bit of algebra to solve for big T. In particular, let's multiply both sides by e to the 2t, right? Or divide both sides by e to the minus 2t, whichever way you want to look at it. So we have t is 10 plus c divided by e to the minus 2t. On the 10, they cancel, right? The e to the minus 2t's cancel on the 10. So I get 10 plus c e to the 2t. Because I have a negative exponent in the denominator, there's no reason to leave it down there. Just bring it up to the numerator and make it positive. And this is great because we got the same thing as separation of variables, right? Same general solution. We have 10 plus c times e to the 2t via integrating factors. It was also the same function that we got when or same family of functions we got when we did separation of variables. 10 plus c times e to the 2t. This is good. If they're both valid methods, they should be giving compatible results. So there's our second check box. So there's 2 techniques for solving differential equations. Great. Thank you. And we'll continue with more ways to solve differential equations soon.